All right. Hello, everyone, and welcome to our February edition of Astronomy on Tap. Hello, can everyone hear me okay? Hello, can everyone hear me okay? Hello, can everyone hear me okay? Hello, absolutely, I can. Hello, hello, testing. Okay, all right. Hello, let's try this one more time. Hello, everyone. Welcome to our February edition of Astronomy on... Oh, shoot. This is not Astronomy on Tap. Sorry about that. This is Astronomy on... We have a lot of events around here that we do. It just gets kind of hectic, you know. That's armadillos. No. Astronomy on Tap. Hello, everyone, and thank you so much for coming. This is AOT. So much that we see you at the next one as well. I'm Alex, and I'll be your MC for today. Is an exciting day to be having an Astro on Tap because just a few hours ago, the NASA Perseverance successfully touched down on the Martian surface. The rover is NASA's first with specialized tools to look for biosignatures in the soil of the red planet and to prepare a few samples for us to bring back and investigate in detail. But in perhaps even bigger news, Krispy Kreme released a donut just for today in honor of the Martian landing. Unfortunately for all of us in Champaign-Urbana, the closest Krispy Kreme is around 57 minutes away. And the reason I know this is because this morning I drove there and I picked up my very own Krispy Kreme Martian donut for today. They say you can really taste the regolith, so I'm looking forward to tearing into this a little bit later into the talk. But I'm also going to be drinking, I don't know if you can see this, it's called Transient Ale. And the reason I'm going to be drinking Transient Ale today is because we're here tonight to talk about a different kind of messenger than was sent to Mars. And that's a ghostly messenger from the extreme cosmos. These are neutrinos, particles that pass through you imperceptibly by the trillions every second, and which bear witness to the most extreme locales in the cosmos, from the interior of the Earth to the hearts of the stars to the Big Bang itself. And here to teach us all about this is Professor Brian Fields, a faculty member of the University of Illinois Astronomy and Physics departments, who is fascinated by the interspace, outer space connections that link the science at the smallest and the largest scales. We encourage you to ask questions at any time. Please ask questions and interact as much as possible. I'll be monitoring the YouTube chat, so I'll be able to read out any questions to Brian as they come up. So without further ado, Brian, why don't you take it away?
Great. So good. So first, can you hear me?
Sound great.
Great. All right. Then, well, thank you, Alex, for the kind introduction, and thank you all for coming to the talk. And I'm very sorry that we can't do this in person to really have astronomy, on tap. But I certainly hope that you're taking the on tap portion of the proceedings as seriously as you would like. So, just as Alex said, tonight we will talk about neutrinos, which are subatomic particles, and they are my all-time favorite particles. And so tonight I hope to give you a sense of what they are and why I think they're so awesome. And so if you don't already know what a neutrino is, then you are the ideal person to be listening to this talk. And I also cannot emphasize enough that I'd really like you to interrupt with questions. That's the deal. If you don't understand, there are no prerequisites for this talk. So if you don't understand, that means I'm doing something wrong and I want to fix it. And the only way for me to know that I need to fix it is for you to ask questions. And it's only fair because, as you will see, I will ask questions of you. So So we're talking about neutrinos, and it turns out that neutrinos are really a mystery story that will start out in inner space, but then take us to outer space. And so we'll be making that journey from inner space to outer space, and there will also be poetry along the way. All right, so we begin our journey in inner space, the microscopic world. And so to make sure that we're all on the same page as we sip our beverages, let's talk about the structure of matter and at its most smallest, most microscopic detail. So ordinary matter, like this apple here, of course, is made of atoms. So that's an artist's conception of an atom, where we have these electrons. I've drawn a carbon atom that's part of this apple. And so it's got electrons, 6 of them here. Those are these little red things in this cartoon. And they're all buzzing around this object. And that object, so I now zoom in again. First, by the way, the first zoom was by about a factor of 1 billion. And now the second zoom, I'm moving in even more by a little under a factor of a million. And then we see that this tiny nucleus is in fact made of 2 kinds of particles. One, which I'll color in blue, those are protons. And then these things in gray those are the neutrons. And so together the protons and neutrons make up the nucleus, and then they're surrounded by these buzzing electrons. Okay, so far so good. Right. So 100 years ago, there was a great revolution in understanding the microscopic world, and how atoms work and what their pieces, these protons, neutrons, and electrons, how they all interact with each other. And I said this is a mystery story, and there are several mysteries, and let's begin with this mystery of the missing energy. And so a subject that'll be important for us today is radioactive decay. And the picture here is Marie Curie, who is one of the pioneers in studying radioactive decay, and she got 2 Nobel Prizes for teaching us how radioactivity works and showing us that radioactivity is what happens when something is unstable and transforms into a new stable state. And what Marie Curie showed is that these kind of transformations can happen when one element, one kind of atom, really one kind of nucleus, then transforms, is unstable, and then spontaneously transforms into another kind of nucleus, then changing from one element to a new kind of element. So it's alchemy in the laboratory. Now, it turns out when one nucleus changes to another nucleus, there's a very definite amount of energy that's released. That's something that we can calculate quite accurately. But when people studied radioactivity, and so to give you an example, let's give you the simplest possible example of radioactivity, where I don't even have a whole nucleus, I just have one particle from a nucleus, so we just have a neutron. So if a neutron is by itself, not living in a nucleus, just by itself, it turns out free neutrons alone are in fact unstable. They themselves are radioactive, and a neutron left to its own devices will decay to a proton and an electron. And this was known back in the day. And in general, the proton and electron will be moving. That's what those little arrows are supposed to be, that they're in general moving. So that's the radioactive decay of a neutron. And a definite amount of energy is released. When a proton changes to, a neutron rather, changes to a proton and electron, it releases a definite amount of energy that we know how much that is. It's related to the masses of these particles. And because there's a definite amount of energy, it turns out what that means is that the electron, which is the easier thing to measure here, it should be moving at a definite speed, which is the same as saying it has a definite amount of energy. And so that's what this little arrow is supposed to be. It's moving off at some speed. So that's what's supposed to happen. But then when people did the measurements and looked at radioactive decay like this, what they in fact found was that the electron doesn't have just a single speed every time you find one of these decays, but instead, for different neutron decays, so each individual neutron decay, the electron has some speed, but if you look at the speeds from one decay to the other, keep measuring it, they're not all the same speed. In fact, they can have a wide range of speeds. So in my little cartoon here, there's one speed, there's another speed's a little slower, there's another speed slower still. So they have a wide range of speeds, not a single speed. And the energy the electron has is always less than the expected amount. It's never more, but it's always less. So they're supposed to have a definite speed, definite energy, and they always have less. Sometimes close to the expected amount, but never more than, and sometimes considerably less. So that's the situation. That's what the experiments told us. And so, since the electron, and it turns out the proton as well, have less energy than was expected, that means the total energy after the decay, that is the total energy from the proton and the electron, is then less than the total energy before, which is just what was in the neutron to begin with. So we have this inequality that I've colored in yellow here because it's a big deal. Because the fact that those books don't balance, that the energy after is less than the energy before, is a complete crisis. It's a disaster. So that leads me to my first question for you. Why is that such a big deal? Now it's your turn.
Feel free to drop your ideas in the chat if you have them.
Yes, that's the way I know your answer.
Cassidy says, what happened to the energy?
Very good. What happened to the energy? Exactly so. So one of the fundamental ideas of physics that teaches us is that energy is conserved. So that is, if we look at the total energy of a system, then that's supposed to be the same over time. So the energy can change forms, it can move from one place to the other, but if you add up all the energy at one time and you wait, let the system do whatever it wants to do, but if you look at all the pieces, parts, and then look again later, no matter what happens, the total amount of energy is supposed to be the same. That's what it means to say energy is conserved. But that's not what it is, apparently not what is happening here. The total energy before is not the same as the total energy after. Energy is not conserved. So that is that's a terrible thing. That's a disaster. Because this is this thing that's worked so well in physics for centuries, and here we are about 100 years ago. They say, "Oh my goodness, it looks like that's not true," and that was a crisis that was really viewed as a crisis, and people considered possible solutions. And there are actually at least two possible solutions to this problem, possible resolutions to this crisis. So anybody want to take a stab at that? I'll give you a minute. Any takers?
So what might have happened to the missing energy? What are we thinking?
Yeah.
We have converted into light or sound, and we have extra dimensions, says Paul Ricker.
Awesome. Very good. We got a heckler. All right, very good. Excellent. So those are both excellent guesses. So converted into light or sound. And those are absolutely excellent guesses. So it turns out so I haven't given you enough information. That is actually an excellent guess, and that's the very first thing people look for. So light or sound, which would be sort of vibrations, those are things we're capable of measuring, and people look very carefully, and that definitely was not the case. So that's a great idea, and people look for that, and it is not the case. Light or sound does not work, but people tried. It's a great idea. It just turns out that's not what the experiment showed was going on. Extra dimensions, I don't know how to answer that question, but what it gets at is it's this idea that, well, maybe that, and you all are with me on this, of course the energy must be conserved, so it just must have gone someplace we didn't notice. In fact, people even consider the idea maybe energy isn't conserved when you get to the microscopic scale. But I'm glad to see that your inclination is like mine to not go there right away. But this was a big problem, and so that led to this. So one of the most famous physicists of the day, the great theoretical physicist Wolfgang Pauly, was pondering this problem and came up with what he called, his words, a desperate remedy. And so he proposed this idea in a physics meeting. He couldn't go to the meeting, but he sent a letter. And so he was in Switzerland, so it's dated Zurich on the 4th of December, 1930. So it's about 90 years ago. And it's in German, but so it begins, Liebe radioaktive Damen und Herren. So dear radioactive ladies and gentlemen. So I already, I like his sense of humor, which is very biting, in fact. So that's how he begins his letter to his colleagues, his radioactive colleagues. And what he proposed, he said, look, we've got to save energy conservation. So like you, he wants to save energy conservation. So he said, the energy has to go somewhere. So he proposes that it goes to a new particle, not light or sound that we could have measured, but something else, some other particle we don't measure. It's there, but we're not measuring it. And so the idea is the neutron decays to the proton and electron, like I said, but there's another particle that we missed. It was there, but we missed it. So that's his proposal. And so one more, annoying question for me. So if we take this proposal seriously, we can already say a few things about about what this particle, what it should be like. So let me get you started. One question you can ask is, what's its electric charge? So you have to remember a little bit about. Anybody want to take a guess? And while you're thinking about it, remember the way atoms work is protons are positively charged. Electrons have exactly the same amount of charge, but it's negative, and that's how they attract each other.
We have one comment in the chat, no charge.
No charge, exactly right. Exactly right.
Two comments in the chat.
No very charge. Good. So there has to be no electric charge because the neutron has no electric charge. It's neutral, that's why it got its name. And so we started out with no electrical charge. We make a charge +1 and -1, which exactly cancel each other. So we don't have room for any extra charge. So this new thing better be electrically neutral. You can in fact say a few other things. It has to have a small mass that maybe not be so obvious, but basically because mass is a form of energy and we can't have a lot of extra energy floating around here. So it can't have a whole lot of mass. And it's never been seen before. We're missing it. We didn't even know it was there. And so it must interact very weakly because it didn't get our attention already. The way electrons interact all the time, and we noticed them and we discovered them. We hadn't discovered this by the 1930s, so it better be weakly interacting. All right?
Brian, we have one more question in the chat, and that is, does this same methodology explain where dark energy came from?
What a good question. And that's something I was hoping to sort of mumble about it into the talk. So this is exactly the sort of reasoning that leads to ideas like dark matter and dark energy, where we see we're missing something, and then you got to propose what could be there, and you propose it's some form of particle. In fact, that's exactly the reasoning for dark matter. Turns out dark energy is even crazier than that. Because it acts too strange to be a particle. But that's exactly the kind of reasoning that goes on. And that analogy is very important. It's a brilliant question. Thank you. So now, so far, remember, this is just a desperate remedy. This is something that that Pauly proposes in a letter to colleagues, right? And he himself calls it desperate. And in fact, he goes on to have this great quote. When he refers to this idea afterwards, he says, I've done a terrible thing. I've postulated a particle that cannot be detected. Because after all, if it's so weakly interacting, we didn't even notice it. how will we ever test this idea? And so he says, I'm a terrible theorist because I predicted something you can't test. All right. But in fact, people were more clever than that. So let's move on. That was 1930. Now we're still a long time ago. Let's go on to 1934. And this gentleman, Enrico Fermi, at the time, I believe he was in Italy, but he soon moved to this great state of Illinois in Chicago. And he ran with this idea from Pauly and dressed it up into a full-on mathematical theory of radioactive decay. So if you like, a theory of ghosts. And his theory went like this. So he created a mathematical theory. I won't bore you with the equations. I'll just tell you the result. It made a bunch of predictions, and all of those predictions agreed with experiment. It was a very impressive theory. In fact, it's so impressive, we still use it today. So to this day, we still use Fermi's theory. We dress it up a little bit, but the basic ideas are still Fermi's. But when he invented this theory, it required him to use a new particle. It required him to take up Pauly's idea that there would be a new particle, that it's essential to the theory. The theory doesn't work if the particle isn't there. And this is Pauly's particle, except Fermi gave it a name, and he's Italian, so he called it neutrino, which is Italian for little neutral one. Actually, because Pauly had actually called it the neutron, but we already had that, so that's not going to work. So he called it neutrino. So Fermi names this new particle neutrino, and it has this nice little Greek nu. So that's not a V, that's a Greek letter nu. That's its nickname. Okay, so he's got this beautiful theory. It agrees really well with experiment to describe all known radioactivity experiments, but for this theory to work, there must be these crazy neutrino particles, or else the whole theory doesn't even work. Because the theory was so successful in all of its predictions, except neutrinos, frankly, quickly, everybody in physics agreed this neutrino must exist, but they were kind of putting their faith in this mathematical theory. They hadn't actually measured them yet. All right. Oh, yeah. And the reason it's hard to measure them is within Fermi's theory, he could tell you why they're hard to measure. In his theory, he said, look, you would, to block a neutrino, to catch it, you could stop it with lead if you want. You know, that's how we stop gamma rays or things like that. But unfortunately, they're so weakly interacting, our neutrinos, that to stop them, you would need lead that is 1 light year thick. That would go a good chunk of the distance to the next star. That's how much lead you would need to finally catch a neutrino, which is just an insane amount. So that means you could make the whole Earth out of lead and it wouldn't stop neutrinos. That's how insanely weakly interacting these things are, which is also explains why we haven't seen them so far, if you believe the theory. And so this is not a direct quote, I'm paraphrasing, but what Fermi's theory teaches us is, if you believe this theory, then where there is radioactivity, which is to say when neutrons and protons interchange, then there must be neutrinos. That's how the theory works. Okay, great. So we're still in theory land though. That's in the 1930s. Now we move on to the 1950s. So we're still in black and white, but we'd be out of that soon. And now the experimental physicists wanted in on the game. They said, what do we got to do to see these neutrinos? How can we really believe these neutrinos are real and not just trust these crazy theorists? And so they came up with this amazing idea called Project Poltergeist, playing off the idea that these things are ghostly. And so there are these two gentlemen, Clyde Cowan and Fred Reines, they kind of led the charge. And so their idea is, if these neutrinos are real, we want to see them in some way. We want to measure their effects. And so, well, first of all, we're going to need an intense source of neutrinos if we're trying to measure them. And then what we'll do, once we know we have a source of neutrinos, or where there ought to be neutrinos, we will let them create radioactivity. So here's how this works. It's kind of the flip side of what we saw before. So before we saw a neutron can become a proton by emitting neutrino, but you can go the other way. If you can have neutrinos around, a proton can absorb a neutrino if the neutrino has enough energy, and boom, changes it into a neutron. It actually also spits out another particle, which is not an electron, but its antimatter partner, a positron, a positively charged electron. So see what I just did there? I dropped in the idea of antimatter. But the important thing for here is that we start with neutrinos. We find a place with a bunch of neutrinos, and then we have a bunch of protons, maybe by having water, which is H2O. So it's got hydrogen, which is protons, and then let the protons change to neutrons and positrons, and then we can measure the neutrons and positrons. We know how to measure those, and this gizmo here is designed to measure neutrons and positrons. So the neat thing is we start with neutrinos, which are hard to see, but we have them convert our protons into things we can see. And then we go look, are they there or not? All right. So that's the idea. But remember, to do this, we need an intense source of neutrinos. Well, what are we going to do? Where are we going to find intense neutrino sources that are available in the 1950s? Well, if you think about it, wait, neutrinos come from radioactivity. Remember, I showed you neutrons decay and make neutrinos. So we want a lot of radioactivity. So we're in the 1950s, we want a lot of radioactivity. And there are basically two ways, if you live in the 1950s, there are two ways to get a lot of radioactivity. So unless someone has already jumped in, I'll go ahead and clue you in. Yeah, so it turns out one way is to have a nuclear bomb. So nuclear bombs create a lot of radioactivity all in one place. So they create a lot of, if there are neutrinos, they create a lot of neutrinos. The other way is a nuclear reactor. So that's a more controlled environment, but because they're filled with radioactivity, they also are intense sources of neutrinos. And so Clyde and Fred were aware of this, and they actually first seriously considered putting their detector device right by a nuclear bomb test. They realized this would cause a lot of problems because then you got to read out the data before the device is destroyed by the very explosion that caused the neutrinos. And in the end, they found it was actually smarter to just go to a nuclear reactor. And then that's exactly what they did. They put their detector right by a nuclear reactor, and here's the result. Well, here is them describing their result, not in a scientific article, but this is them sending a telegram to Professor Wolfgang Pauly in Zurich. Remember, that's where he is. And here's their telegram. I'll just read part of it. We are happy to inform you that we have definitely detected neutrinos. And they go on, they're changing protons. And for the experts in the audience, they even report the cross section. So that's very nice of them. So that's wonderful. So they actually did the experiment. They went to the nuclear reactor, and lo and behold, suddenly out of nowhere, neutrons and positrons started appearing in their detector, just as was predicted, exactly at the level that was predicted. So Pauly responds to this, and he's totally cold-blooded about it. So he writes to Reines and Coulomb and says, thank you for your message. Everything comes to him who knows how to wait. So he's just totally cool. So he makes his prediction in 1930. Here they are. It's 1956, and they measure it, and he's like, of course they're there. Of course, I knew it all along. So he did not lack for self-confidence, Pauly. So now we have experimental proof that neutrinos are real. All right, great. So, oh yeah. So before we move on to outer space, I did want to have one interlude to mention bananas. So now we all know bananas are delicious. That's obvious. And they're also nutritious, as you know. So why are they nutritious? I mean, what are bananas famous for? Not a trick question, just keeping you in the game.
We have potassium and
bravo.
Potassium and nutritious spelled like neutron or neutrino.
Oh, that is an awesome. Oh, I'm going to steal that. Thank you very much. That's a great line. But yes, they are filled with potassium. Now, there's a fun fact. It just turns out that about 0.01% of all natural potassium, ordinary potassium, is in fact radioactive. It's a radioactive version of potassium. For the expert, it's called potassium 40. So in any amount of potassium, about 0.01%, so 1 part in 10,000, is radioactive. That's just true. That's just the world was born with this stuff, and it's still here, and it's radioactive. That's just the way it is. And it's radioactive, so that means it wants to transform. That's what radioactivity does. And when it transforms, our potassium changes to calcium. So the element changes, just like Marie Curie told us, and it emits an electron and a neutrino. All right. So, but that means something. So that means if you have some bananas, what it means is the bananas emit neutrinos. And in fact, if you do the math, they emit about 10 neutrinos every second. So bananas have 10 radioactive decays about every second. So that's actually not very much. They're not very dangerous. In fact, they're perfectly healthy. But that also means that they generate 10 neutrinos every second. So bananas are neutrino sources, and you get about 10 every second. But the reason we eat bananas is because we need neutrinos, and so we emit neutrinos. In fact, we have more potassium than a banana, so we emit neutrinos. It depends on how much of you there is, but for an average sized person, you emit about 100 neutrinos every second just from the potassium in your body. So you are a neutrino source. It's not no disrespect, me too. We all are neutrino sources, and we should be, because we should have potassium. You need it, it's good for you. So we have skin in the game. We all are neutrino emitters. So no worries, it's natural, it's always been there, and this is very low level radioactivity. It's nothing to worry about. It's perfectly healthy. You know, don't eat uranium, but potassium's good for you. Yeah.
Brian, we have a question in the chat.
Please.
It's maybe a technical question. How do you distinguish between beta decay and neutrino capture?
Ah, very good. And at the level I'm talking in this talk, I've been a bit sloppy about all of those. The neutrinos I've been talking are mostly from beta decays, but the thing I just showed you in the Reines-Cowan experiment, that was a neutrino capture. Yeah. So I'll for the experts, I'll try to slip in little remarks like that. But the basic idea is always the same, that the neutrino is encouraging neutrons and protons to interchange. Okay, very good. All right, so before we go on, we're about to go on to outer, we've done inner space, we're about to go to outer space. So, but before we go on, questions so far? You've been good at answering my question. If nothing else, it gives people a break. Yeah. We good?
I think we're good in the chat so far.
All right, then we will move on. All right, so now we move on to outer space. So now that we know neutrinos are real, then we got to talk about what our universe is like, and from the point of view of neutrinos. All right, so charity begins at home. So we're going to start within the solar system. So historically, this is the first example where people thought a lot about neutrinos and the cosmos, and that's to do with stars, particularly the sun, but in fact for stars in general. All right, so this is a good chance for me to remind you about some of the basics of stars. So I'm going to warm you up by mentioning a few simple facts about stars like the sun. This is a picture of the sun. A few facts about stars like the sun. And these are actually not very, they won't be big surprises. These are things you already know, but I'm going someplace with this. So first, stars always lose energy. I'm always interested in energy. Stars constantly lose energy, by which I mean stars are throwing energy out in space, mostly in the form of the light they emit, because after all, like the solar power that we use to heat your house in a green way, that energy comes ultimately from the sun, which means the sun had to emit it in the first place. It had to leave the sun. So stars are constantly throwing energy in this space in the form of the light they emit. All right. Second, stars have a finite amount of mass, a finite amount of stuff in them. When I say finite, I don't mean a small amount. I just mean they don't have an infinite amount. That's all I mean by that. Stars actually have quite a bit of mass, but not an infinite amount. So that means that whatever the fuel supply is in a star to keep it nice and lit up, whatever that fuel supply is, they have a finite amount of it, a not infinite amount, which means they've got a limited energy supply. All right. Finally, as we already discussed, energy is conserved, which is sometimes also rephrased. There's no free lunch. So you can move energy from one place to the other, but you can't just make it out of nothing. Okay. So none of those three facts are particularly surprising to you, but the fun part of this is you put them all together. So string those three facts together, and then you get to an uncomfortable conclusion. So now it's your turn. The stars are losing energy. They have a limited amount of energy in them, and energy is conserved.
It's gonna die. That's what we have.
Very good. Stars can't live forever. So this is a game that cannot go on forever. So they're pouring energy out into space. They've only got a certain amount in reserve, and once that's gone, it's gone. And so that exactly means all stars must die. You can in fact even go another step. All stars must die, and they can't live forever. So that means the sun is going to die, which is a bummer. The fortunate news I can tell you is we have another about 4 billion, 5 billion years to go before the sun dies. So don't, there are things to worry about in 2021, but this is not, death of the sun is not one of them. But because stars don't live forever, and yet there are stars in the sky today, that tells you that they can't have been here forever. That means at some point they had to be born, which means stars have life cycles. So just like people and dogs, stars are born, live their lives, and then die. Stars have life cycles. And depending on how much time we get in today, we'll talk about some of that life cycle. But let's start with the sun. Like I said, charity begins at home. Let's start with the sun itself. So how does the sun shine? So a great mystery in history was what powers the sun? How can the sun stay lit up? So this is a picture from the sun from yesterday. Taken from space. There's a NASA satellite. So what powers the sun? So the sun is supposed to stay lit for billions of years. The Earth has already lived billions of years. We want it to live billions of years more. How does the sun manage to stay lit up for that long? And so people pondered this. And in the 1930s, it was a great time back then, they proposed that the sun is powered by nuclear fusion, by smashing together hydrogen and getting helium. So here's the idea. Hydrogen is really, at its guts, is made of little protons. The idea is 4 protons are smashed together. There's a whole series of reactions that do this, but the main point is you start with 4 protons and you smash them together. And at the end of the day, these 4 protons are all stuck together and they make a nucleus of helium. So we start with hydrogen, which is protons, and we end up with helium. So that's another transformation where we take one element and we get another element. Awesome. But notice, in this particular form of helium, as you'll notice, it has 2 protons and 2 neutrons. So we start with 4 protons and we end up with 2 protons and 2 neutrons. Great. But if you scratch your head, you say, wait a minute, that can't be the full story. Something's missing here. I haven't written down everything that you get at the end of this. So we do start with 4 protons, but at the end we get helium plus something else. So I haven't balanced the books. We need some more particles. Now it's your turn.
We have missing some positive charges.
Good.
We have electrons.
Excellent. Very good.
The electrons.
Very good. So notice we started with 4 positive charges. Now we only have 2. So we've got some positive charges. We have to conserve electric charge. So we're going to need some positive charges. And also we've got protons that became neutrons. And remember what Fermi taught us. If protons are changing to neutrons, there's got to be a neutrino around as part of the crime. So there we go. So in fact, we're missing 2 positive charges, which are positive electrons. These are these antimatter positron things. That's a whole story by itself. But also because we changed two protons to neutrons, we need 2 neutrinos as a result. So there we go. So that's the theory, that if nuclear fusion is going on, it should be changing hydrogen to helium and should be making positrons and neutrinos along the way. So we would like to test that. All right. Well, how are we going to test that? The idea is that the sun's supposed to host nuclear reactions. How do we know that? Well, the way we can test, of course, is to look for the neutrinos. Of course, I'm going to say that. They're my favorite particle. So if this little theory is right, the sun is emitting a blizzard of neutrinos, which we would like to see. So the way you do this, and now we're getting up to my lifetime. Now we're getting up to the 1960s before people say, well, that would be cool to look for. Well, the way to do this is in huge experiments underground. And we need them to be huge, and we need them to be underground. I won't torment you too much. Let me just explain. Well, remember, we saw that it's really hard to catch a neutrino. And so that's why the experiment has to be huge. Most neutrinos just go straight through the experiment. So we need as much experiment as we can, the biggest target we possibly can, to have some meager chance of catching a few. We'll miss most of them, but we just need to catch a few to find out that they are there. And we need them underground because it turns out we're constantly bombarded by other crazy particles from space. They're called cosmic rays, that on the surface of the Earth, we're bombarded by them. And it's going to be hard enough to measure these crazy neutrino particles and the reactions they cause. I don't want to be confused by other things going on. So you go underground to get away from these nasty cosmic rays. All right. So it turns out there's several ways to measure these neutrinos. People are very clever. They came up with several ways. So the first way that was done in the 60s, so now we're up to the 60s, is the following thing. So now we go to South Dakota, and there's a gold mine there. It's literally a gold mine, but they let one cavern in here, and here's the cavern. They lent it to the physicists, and here are two of them. And in this cavern, they put a giant vat here. You can see it's enormous because you can see the people. And they filled it with, well, basically chlorine, which is in the form of dry cleaning fluid. So they bought out a good chunk of the available dry cleaning fluid and filled this giant tank with it. And the reason they did that is because it turns out what neutrinos like to do, once in a while, they mostly do nothing, but once in a while, if they hit chlorine, they will change the element to argon. So this is another one of those radioactive, this is neutrino capture again. So they change the element from chlorine to argon. And the idea is argon, chlorine is part of the liquid in here, but argon is always a gas. And so then with incredible chemical techniques, they could collect individual argon atoms, which are themselves radioactive, and then they can watch it decay and convince themselves they found the argon. And so just like our friends Coulomb and Reines found neutrons from radioactivity from neutrinos, here we're finding argon atoms from radioactivity from neutrinos. And
Ryan, maybe this is a good time to jump back. We had a question in the chat. If neutrinos don't interact with matter, what causes radioactive damage?
Oh, so neutrinos interact once in a while with matter, but very, very, very rarely. But yeah, so what the reason radioactivity is dangerous, the reason you don't want to, you can eat bananas because they have tiny amounts of radioactivity, but you do not go eating uranium. And the reason for that is the neutrinos don't hurt you. The neutrinos come straight out. If it were only neutrinos, we'd be fine. We wouldn't care about radioactivity at all. We wouldn't be scared of it. But remember, the radioactivity also emits this high energy electron. It didn't have as much energy as we thought it would have if there were no neutrinos, but it still has lots of energy. And those high energy electrons are bad news. They are very damaging to your cells. At the microscopic level or in the atomic level, they are very damaging to your cells. And that is, one high energy electron is no big deal, but if you have a whole bunch of uranium in you, that's a lot of high energy electrons, and that's catastrophically damaging to your cells. And that's why you have to be very serious about radioactivity for large amount of radioactivity. But a few decays a second, believe me, is no big deal at all. That's why bananas are perfectly healthy and you should eat them. But eating uranium is no joke at all. Yeah. But the neutrinos themselves are completely harmless because we have to build experiments this big to even catch one of them per day. So, which is the rate this would detect them. And so, oh yeah, and this is the guy who did that. There's another way to detect neutrinos, where you build a big tank of water. So the first one was built in Japan. So this happens to be in Japan. They build an enormous tank of water deep in a mine, and then it's a little bit hard to tell. This little dot, that's a raft. And those are people in clean room suits. And what they're doing, all these little dots, or these little bubble things, are little detectors that can detect flashes of light. And they're surrounded by a plastic coating that keeps them from getting wet in the water. And so they're in a raft, and they have to go around and check every one of these. And you can see that's a huge job, which means these are graduate students doing the work. The professors aren't doing this. And the reason you do all of this is in this big tank of water, a neutrino comes along, and it turns out the neutrino can kick an electron. So an electron that's sitting around, maybe in a hydrogen atom in the water, is suddenly hit by a neutrino screaming in from the sun, and suddenly the electron is given a big kick by the neutrino and is suddenly launched at high speeds, moving nearly the speed of light. And when the and this is that's damaging. And one of the things, the reason these high energy electrons are damaging is it emits big flashes of light. It's causing all kinds of damage. And we can see these flashes of light. That's what all these little dots are. They're detectors ready to see these flashes of light from electrons that have been kicked by the neutrinos. And the neat thing is, the electron is kicked in a definite direction and it creates a little ring of light. And you can see that ring in the detectors. That's what that little image is. Okay. There's a similar thing you can do. Oh yeah, so this is a different detector where we start with heavy water. It changes and the heavy water is broken apart into neutrons and protons. This is yet another way of doing it, and yet another way still. This is in Italy, where you have the neutrino kicked an electron, but you measure it not in water but in a sort of carbon liquid. But they're all the same basic idea. You either see a radioactive change in what the stuff is made of, or you see an electron get a big kick and move at high speeds and make a flash of light. The results, I just want to give you an idea of all the crazy experiments we build to do this. And the result is all of these experiments detect neutrinos. And furthermore, when you detect them, I told you some of the experiments give you an idea of where the neutrino came from. And then you can ask the question, every time I see a neutrino, I look at the direction it came from and ask, what is in that direction? In particular, where is the sun? And so the picture here is a map where I map out where I saw all the neutrinos. So every neutrino would be a little dot. And if I have more, if I see very few, it's only blue. If I see none, it's black. And if I see a lot, it's red. And I see the most, it's white. And so it's just a map of where I see all the neutrinos, and the center of the map is where the sun is. So at any given time, I ask, where's the neutrino compared to where the sun is? And of course, they all pile up in the center. That's telling us all the neutrinos come from the sun. So this is a map of where the neutrinos come from. In our experiment, we see neutrinos and they all come from the sun. And so that's amazing. We not only detect neutrinos, but we can verify they really come from the sun. So that's amazing. So first, that immediately tells us the sun is powered by nuclear fusion. Neutrinos come out of nuclear reactions. And so that tells us, and they come from the sun, so that tells us nuclear reactions are going on in the sun. But there's even more. This map of neutrinos from the sun, you could describe it more simply as I have at the caption at the bottom. This is an image of the sun taken with neutrinos. This is a picture of the sun taken with neutrinos. To say it yet again, I have used these crazy water tanks as telescopes to take pictures of the sun. So these experiments, you can view them as neutrino telescopes. They're nothing like a tube you put your eye in, but they really are telescopes. They probe the universe. And so these experiments mark the birth of neutrino astronomy, observing the cosmos with neutrinos. And they verify that you are bathed in neutrino shine from the sun both day and night, because most of the neutrinos come straight through the Earth. And I'd like to contrast what we learn from neutrinos versus what we learn from sunlight. Sunlight tells us about the surface of the sun, which, although it's quite crispy, the surface of the sun is actually the coldest part of the sun. It only gets hotter as you go inside. And the surface of the sun is where the sun's energy is finally lost to the rest of the world, the rest of the cosmos. Neutrinos, on the other hand, probe the core of the sun. That's the hottest part, and that's where the energy is created. So by looking at both, we get a full picture of the sun. So the neutrinos give us the rest of the story. That's what's so powerful about the neutrinos. All right?
Right.
Very good. Oh, question.
The image is slightly, it's not completely spherically symmetric. It's like it's longer in one direction than the other. What causes that?
Good eye. Yeah. So I think so I've seen other versions of this. So some of these are just this is a pretty noisy image. In fact, this the blob you're seeing, the size of the blob is actually completely noise. I said we can get an idea of the neutrino direction, but it turns out we can't do a very good job of it. That's actually quite hard to measure. So this blob is it's sort of it's like looking Coke bottle glasses at the sun. The actual disk of the sun is smaller than the little white blob here, but this is just telling us the smearing of our Coke bottle glasses. So and so the randomness of that smearing leads to the effect you're seeing here. But in fact, the map is all they all are concentrated in the sun. They're not extended in one direction versus the other in any meaningful way. Good question. All right, very good. So I promised you some poetry. So now that you've gotten this big dose of all this technical stuff, I'll promise you some poetry. So let's have some poetry now. And so this is a wonderful poem by the writer and sometimes poet John Updike. He's famous for his essays, the Rabbit series novels, but he also wrote some poetry. And as you can see, this poem was written in 1960, and it's called Cosmic Gall. And so I don't have my beret on, but I'll do my best to give a dramatic reading. So it goes like this: neutrinos, they are very small. They have no charge and have no mass and do not interact at all. The Earth is just a silly ball to them through which they simply pass like dust maids down a drafty hall or photons through a sheet of glass. They snub the most exquisite gas, ignore the most substantial wall, cold shoulder steel and sounding brass, insult the stallion in his stall. And, scorning barriers of class, infiltrate you and me. Like tall and painless guillotines, they fall down through our heads into the grass. At night, they enter at Nepal and pierce the lover and his lass from underneath the bed. You call it wonderful, I call it crass. So that is a brilliant poem, but it was written in the 1960s, and we've learned more about neutrinos since this was written. And in fact, there are some important, beautiful things that are correct here, but there are a couple little details that are wrong. So we'll finish with, what did he get wrong? He gets some things right. For example, he says neutrinos have no charge, and that's exactly right. But he gets a couple of things. He gets a couple of things wrong, and they're right at the beginning of the poem. There are a couple of things that aren't quite right. And one I haven't quite said, to tell you the truth. So, all right, I won't torment you more. One thing I didn't really say, he says they have no mass. That's actually not quite true, but from great effort, we now know neutrinos do have mass. Oddly, we can't actually tell you how much, but we know they have mass. Long story. The other thing is, he says they do not interact at all. If they really didn't interact at all ever, we wouldn't even know about them, but they interact just a little bit. It takes tons and tons of lead to stop them, or you have to measure very many, but they hardly interact. So so they have little mass rather than no mass, and they hardly interact at all. And there we go, we cleaned that right up. Okay, so tell you what, in view of the time, let me just do one more thing. Okay, so we're almost out of time. So let me tell you one more story before we finish. So let's go back to, we're almost at the anniversary, to February 23rd of 1987. So that was a great day in astrophysics because there was this great burst of neutrinos. At the time, there were a couple of neutrino detectors working, and they actually were also trying to detect other things, but they functioned as neutrino detectors. This one was in the United States, the other one was in Japan. And suddenly, these things saw a bunch of neutrinos all at once. Now, in the neutrino business, a bunch of neutrinos means like 24. For us, that's a lot. And because normally these things might detect a neutrino a day from the sun. The whole day, they might detect one neutrino all day. It's a tough business measuring neutrinos. But these detectors measured a bunch of neutrinos over a span of 10 seconds. So this is a graph, the only graph I will show that goes from 0 to about 12 seconds. And then there's a little dot every time they saw a neutrino. The Japanese experiment is the one in yellow here. This thing called IMB is in red. And then there's another one as well. It's a Russian experiment. And they all saw these neutrinos all in the span of 10 seconds. And so in the neutrino business, that is an enormous number of neutrinos, and it's incredibly packed in time. So we saw them in 10 seconds, this is an enormous burst of neutrinos. And so what is that? Well, so it turns out that that is something super interesting that suddenly made a bunch of neutrinos all at once. And I'll just tell you, so it turns out exactly at that same time, we saw a star explode, except it wasn't even a star in our own galaxy. It was a star in a sort of neighboring little baby galaxy, for the experts called the Large Magellanic Cloud. So this is a piece of that galaxy, and this is a star that's exploding. It's actually it's becoming ever brighter. This is actually towards the beginning of the explosion. It got much brighter after this. And this thing made neutrinos. So not only did the thing explode, but it actually made neutrinos. So how did it make neutrinos? Oh, by the way, there it is. So this is after, that's before, and this thing made a bunch of neutrinos. And actually really interesting. In the center of the star, it got so incredibly hot that the star itself made matter and antimatter, electrons and positrons, and they annihilated with each other and made neutrinos. It turns out that's a possible thing as well. There's another way of making neutrinos. And so we see those neutrinos. By the way, that also means neutrinos have antiparticles. And it turns out the neutrinos were detected before the light was. So people saw this neutrino burst, and hours later, the actual light was discovered. So the neutrinos actually were found first. And at first, people didn't know what was going on. And that's a whole interesting question. And it turns out it's because neutrinos escape directly from the center of the star, and then they just leave. But the explosion starts at the center of the star and grows outwards, and it takes the explosion time to get to the surface of the star, but the neutrinos are already gone. So that's what this says. Oh, and also this neutrinos, remember, took 10 seconds. So what's that telling us? And it turns out the reason it took 10 seconds, why didn't they come out all at once, is because the center of the star was crushed to such incredible densities that it actually was enough to bottle up the neutrinos. It actually was one of the few places in the universe that is not transparent to neutrinos, and it took them 10 seconds to sort of squirm their way out. And that shows us that the core of the star was an incredibly dense neutron star. And so the neutrinos, once again, probed the heart of affairs. They told us what was going on at the very heart of an exploding star. So, and we'll see if there are any remaining questions about that.
This comes just at the right time because we just got a question in
Oh, good.
the chat. That is, you mentioned.
Oh, no.
Sorry, could you hear me okay?
I could hear not a word. I heard not a single word of the question. I'm so sorry.
Okay. There were discrepancies of various amounts of energies in the decay of a neutron. Are there varying numbers of neutrinos produced, and what causes the varying numbers?
What a great question. Yeah. So each decay produces a definite number of neutrinos. It turns out what I didn't tell you is different kinds of decay, not so much radioactivity decay, but other kinds of particle decays can also produce neutrinos, but it turns out they can come in different varieties. They actually come in 3 different varieties. I could have talked all day about just the physics of neutrinos, but I wanted to do some astro, but it turns out they come in 3 different varieties. But yeah, the number of neutrinos you get out, there's always a definite number of neutrinos, and you always get one, unless there are very special circumstances. There are very special decays, so it's almost always one. There are some very special decays where the situation is just right to get 2 neutrinos out. That's called double beta decay, and those are super interesting things that people study because it turns out they tell you more about how neutrinos work. But yeah, it is not a random number of neutrinos. It's always a very definite number of neutrinos, and that it teaches you something what you measure. Yeah, great question.
Another question we have. So neutrinos get emitted during supernovae. In the huge numbers in which they are generated, could they exert enough pressure to help prevent the supernova from stalling?
Oh yeah. Right. So in fact, that is a great question. So for the non experts, there's a so it turns out the way these massive stars explode is kind of complicated. What they actually first do is they implode. The star runs out of fuel, can't support itself anymore, and against its own gravity, and the star implodes until it crushes itself to incredible densities. That's what the neutrinos were telling us. It gets crushed to incredible densities, and then finally, this incredibly dense core of the star is able to support itself. The rest of the layers, which are still gas, come crashing down at almost the speed of light, and then they're gas, so they bounce back and launch an explosion. That's the basic story, but it turns out that in our computer simulations, it turns out it's easy to say that, but it's hard to make this actually work. And often when this explosion starts, it kind of stalls and it slows down and doesn't proceed to lift off the star and make it go boom. And it remains a great source of study to see what's going on. And indeed, the neutrinos likely play a very important role. And so the study of supernovae is very deeply intertwined with the study of neutrinos, exactly to answer this question. Because nature has clearly figured out how to do this. We just need to teach our computers how to do it.
Great. We have another question. Do they still believe neutrinos change type as they travel or interact with matter?
Yes, these are some of the beautiful topics I didn't have time for because I wanted to let you know about the cosmic aspects of neutrinos, but they absolutely, turns out neutrinos come in 3 varieties. And the interesting thing is they're born one way, but they can change and become something else, which is kind of nice. So they don't just have fixed identities; they change over time in ways that we can predict. And that's easy to say, but that was a big effort to measure that. And actually, measuring neutrinos from the sun is one of the ways we first learned about that. And that's a very peculiar properties. Like electrons don't become other things. It's a very peculiar to neutrinos that they do that. It turns out it's important that they be neutral particles. You only have a chance of doing that if you're a neutral particle. And it turns out through reasoning I don't have time to explain, that's how we know neutrinos have mass. It turns out the only way to do that is to have mass. If they're massless, they don't do that. So that's how we know neutrinos have mass, even though we don't know how much mass they have. So yeah, they're very peculiar things that you can see why neutrinos are fascinating. Just from their physics, they're fascinating, and they're fascinating for astrophysics. And I don't have time to tell you all the ways that they're fascinating for astrophysics. Anything else? I know we're about to time, so maybe if I could just leave with some final thoughts, because I know we're already at 7. I know people have to go. I'm happy to linger for anyone who has remaining questions, but let me just well, here. There's not a final exam, but you can think of more as bonus questions. So I'll just ask the question. I won't make you answer, but just, oh, am I sharing my screen? Yeah, okay, good. So one is neutrinos, mini neutrinos go through you every second. And I picked 2 random people here. This is my way to plug. If you haven't watched The Expanse, Expanse is totally awesome. So these are 2 of my favorite characters from The Expanse. So they're just like you and me. They're being bombarded by neutrinos. How many neutrinos go through you every second? Well, the answer is it's a bunch. It's about 3,000 trillion, which is 10 to the 15 neutrinos. So I've written the number out. That's how many neutrinos go through every second of every day of your life. So you are bathed in neutrinos all the time. A second bonus question is, what is the largest source of those neutrinos? We only had a chance to talk about some of these. So you might imagine it's bananas, the Earth, the sun, supernova explosions, supermassive black holes, or the Big Bang. It turns out all of those contribute to the neutrinos that go through you every second. But by far, the Big Bang is the major source. Although trillions go through you from the sun, that's peanuts compared to the Big Bang. So most of you have all these neutrinos going through you, and most of them came all the way from the Big Bang. All right. So with that said, let me wrap up with some lessons. So remember, neutrinos began as this desperate remedy to solve this energy conservation mystery. and they were this thing that Pauly wouldn't even show his face to make the prediction. And now we know them to be, in fact, they are the most abundant particle in the entire universe. They're more common than any other kind of particle. So the most abundant thing in the universe was totally invisible and unknown to us until 100 years ago. They probe the heart of the most violent events in the universe. We talked about the center of the sun, exploding stars. I didn't get a chance to tell you, but they also come from the interior of the Earth, and they come from these jets that are launched off of supermassive black holes. If we have time afterwards, you're welcome to ask me questions about that. You are awash in neutrinos arising from all of these things, from bananas all the way up to the Big Bang. And you already anticipated this in some of your questions, they are dramatic proof that there's more to the cosmos than meets the eye. And is this kind of thinking that propels us to ask what dark matter is. I think maybe that's another kind of invisible particle. So I just wanted to put in a plug for dark matter. So on that note, thank you all. So we're out of the official time, but I'm happy to stay and answer questions as long as anyone has the patience for them.
Well, thanks, Brian, for that wonderful talk. I have a set of questions that I didn't ask. My internet will stay stable long enough for me to ask them. What is your favorite and least favorite thing about neutrinos?
So I guess I would say that's a great question. No one ever asked that before. My favorite thing is that they sound like science fiction that they're not. 100 years ago, when people were debating about how the sun is powered, if someone had said, he said, we don't understand where the energy comes from, and somebody said, look, there are all these crazy, there aren't really atoms, they're particles smaller than atoms, they're at the center of the sun, they're all colliding, and they're making these invisible particles that go through you by the trillions every second. People would have thought you're crazy, but that turns out to be true. So I love it when something that's science fiction-y like that turns out to be science fact. I just love that. Because that's one of the fun things about science in general and astrophysics in particular, is that that we take the bizarre and we try to make it more commonplace, that we try to see there are simple rules that let you understand things like this. And also we try to take the commonplace and make it sound bizarre too, but that's a separate story. And the most frustrating thing is that they're so hard to measure. The thing that makes them cool also makes them so frustrating that they're so hard to measure, because there's lots of things we don't yet know about them. Just to pick one example, I mentioned matter and antimatter. So that's another major result of 20th century physics. Every particle has an antiparticle. It turns out we don't know the answer to the simple question, what is the antiparticle of a neutrino? In particular, I mean, they must have an antiparticle. The big question is, could the neutrino be its own antiparticle? It turns out that for a lot of things, that's not possible. Anti-electron cannot be the electron because it has the opposite charge, so it can't be the same thing. But if it's a neutral particle, it can be. It's possible, but it doesn't have to be its own antiparticle. Neutrons, for example, are not antineutrons are separate things. The two are different. But another particle you might have heard of, photon, the particles of light, they are their own antiparticle. So it can go either way. And for neutrinos, we actually do not know. It is an open question whether neutrinos and antineutrinos are distinct particles. And we would love to, that has major implications for cosmology. We would love to know the answer to that question.
Great. We have another question. If neutrinos traveled at the speed of light,
I only got it, neutrinos traveling at the speed of light. You guys,
that one more time, potentially.
Or you can copy it in the chat.
If neutrinos travel at the speed of light, sure. Let me drop it down. Oh.
Or I can hear you now. Go ahead. Yeah, just in case it doesn't work.
If neutrinos travel at the speed of light, wouldn't all the neutrinos from the Big Bang have passed through and would now be gone?
Ah, what a great question. Yeah. Okay. That is a super good question. So two things. First, it turns out So there's a lot to that question, and so I'll try to give the Twitter version, but the true answer would take, deserves a longer answer than I'm going to give you. First, I just have to say, because neutrinos have mass, one of the things that means is, it's a Einstein thing, things that have mass can't move quite the speed of light and go as fast as you want, up to the speed of light, but not equal to the speed of light. So they move slower than the speed of light. But that doesn't really affect your question. The neutrinos we're interested are born moving very, very fast. So that doesn't really change your question that much. So the spirit of your question is still exactly on target. And it turns out, so then the question is, they created the Big Bang and then they zoom off in all directions. So haven't they all passed us? And there are many neutrinos that have passed us, because they can certainly go straight through us. They don't stay. The point is that the universe just keeps going on. And so there are always some neutrinos that are just arriving now. And there's a further part of the universe where tomorrow there'll be neutrinos from them at that point arriving to us. And there's a yet further part where there'll be neutrinos arriving the day after. And so, because the universe, as far as we can tell, just keeps going on, there are always more neutrinos that'll come and meet us. And so that's one of the beauties of cosmology. That's a very brief answer to the question, but that actually, it deserves a longer conversation than that. But that's the Twitter version.
Great. Well, I think because we've gone just a little bit over, we will end it there.
Great.
I was hoping to play a little music to play us out, but I think my internet will not hold out. So instead, I'll just link to a song that I've been listening to, which is the song called "A Place in the Sun" by Ingrid Lucia and the Flying Neutrinos. So have a listen to that and think about this wonderful talk if you're feeling so inclined to learn a little bit more about neutrinos. Thank you, everyone, for joining us this evening. Thank you, Brian, for teaching us about neutrinos, these cosmic messengers. And that was our February Astronomy on Tap. We hope you learned something, and we will see you again next month in March. Thanks, everyone, and take care.